Right. Any questions? Okay. Sort of pick up where we left off. Simply the last thing I did was that sort of that flow of you put energy into a system. So let's take a look at some specifics here. Or at least, I guess we'll start out with some vocabulary. So Q stands for heat, of course. I assume Q originally stood for quantity, or whatever the Latin equivalent of quantity is. But this is energy transferred between objects because of temperature difference. So it is possible to have delta Q, but generally Q already is talking about a change in energy. You're transferring energy in, and so you typically do not see a delta in front of Q. So I have some sort of cube right here of a material. And based on my notes, I think I'll probably be using this in just a moment. I have 50 grams of aluminum. There's some sort of energy I put into it, and that is going to cause a change in temperature. In other words, we're getting the particles to move around a little bit faster inside. So sort of a microscopic change in kinetic energy causes a change in temperature. So there should be some relationship between the amount of energy I put in and the change in temperature. The more energy I put in, the greater the change. If I take energy out, I should have a loss of temperature. It should cool down. You could also look at that if I take a hot cube of aluminum and stick it in the room, energy is going to radiate into the room because there's particles that will hit the cube, and because the particles in the cube are moving faster, the particle is going to hit it and bounce back a little bit faster, so the temperature of the room will increase and the temperature of the cube will decrease. So we're transferring energy from cube into the room. So let's talk a little bit about temperature, and then we'll talk about the relationship between Q and delta T. So let's just start out with the SI unit of temperature. What is the international standard? That is a unit that's not the international standard, but and technically it's degrees Celsius.
Kelvin?
There we go. Named after?
Kelvin.
Yeah, Lord Kelvin.
It's not degrees Kelvin, right?
Correct. It's just plain old Kelvin. Now, at this point, I might have transitioned completely over into Celsius. You might occasionally hear me say centigrade instead of Celsius, just because that's what I was taught. And the centigrade, I think, is officially not supposed to be used anymore. But called centigrade because you basically go from freezing to boiling point, and it's broken up into 100 grades, or centi, meaning 100 grades. But this is degrees Celsius. Named after? Yes?
Greek, I guess? Romans?
No, I think he was a Renaissance.
Oh.
So somewhere between the 1400s and 1600s, I think he was around. I could be off on that, but I think he, and it's possible that that was just the name he adapted to make him sound like he had ancient knowledge. And then our unit of system, or unit of measure.
Fahrenheit. Degrees Fahrenheit.
So degrees Celsius, degrees Fahrenheit are the ones that you most run into in the everyday world. Kelvin is what you get more of in science. So these are sort of analogs of each other. This is the everyday world. Kelvin is metric, so these two are very much related to each other. But what is the sort of degree Fahrenheit equivalent or analog of Kelvin? Actually, before we do that, let me give a little bit of background here. So degrees Celsius is based upon 0 degrees Celsius is freezing of water, 100 degrees Celsius, boiling water, boiling point of water. Fahrenheit system was set up where 32 degrees Fahrenheit is freezing of water, and 212 degrees Fahrenheit is boiling. So the question is, I mean, this makes sense. Water is sort of universal. Thank you. So you can set up a scale here that everyone should be able to get 0 and 100. We established a scale that's pretty much worldwide. But 32 and 212? What's going on there? How on earth did he come up with that? Anyone know? The coldest thing that he could make, he established as 0. So there was some sort of, I think it was a salt-water combination, which he left outside. So the coldest thing that he could create, he established as 0. And then the other number that he established was, I think it was body temperature, which he set at 96. Obviously, he was either a little chilled that day, or the scale has changed slightly over the years. But 96, what's so special about 96? Think back to Babylonians and the number 60. What was special about 60? And more than that, yeah. It's the fact that 96, a lot of things go into 96, and so that was one of the reasons for picking 96. It in theory, made the math easier. And then over time, things have shifted slightly. By the way, what is the normal body temperature? What's average human body temperature right now?
It's like 98, yeah.
Pardon?
98.
So where does 98.6 come from? I think officially it's 97.9, but 98.6 is that classic body temperature. Where does that come from when that's actually not the average?
Does that depend on where you live?
Almost. Not where. When?
I was going to say when, but it makes sense.
98.6 came out. I kept wondering this because, you go into a doctor's office nowadays and they say, have you had a fever? And I'm going, all right, what's a fever? And to them, it's above, what, 101? Or above 100?
Well, life rate is like 199 or 100.
Okay. So I kept wondering what's 98.6 because I flashed back to elementary school. I was feeling sick and I went into the nurse's office. She took my temperature. It was 98.4. She said, well, you don't have a fever because it wasn't 98.6. And my body temperature typically is below 98. So
That was a fever for you.
yeah, But 98.6, they did a sampling of people in Europe in the mid-1800s, and the average body temperature was 98.6. That's where that comes from. So I've read. And there's some explanations, I can't remember what they are, but there were some explanations for why the average body temperature of humans now is less than it was 150 years ago. So anyway, all right, so we have a scale here set up for Celsius and for Fahrenheit. Kelvin, so if I have a gas and I start to slow the particles down, in other words, if speed goes down, kinetic energy goes down. And they thought, well, what happens if all the particles stop moving? Then what's the total kinetic energy?
0.
Yes. So they figured, well, you can't get lower than that. And since kinetic energy and temperature are definitely connected to each other, they established 0 Kelvin is when everything stops. This is what they call absolute zero. It is the equivalent of negative 273.15 degrees Celsius. Matter of fact, the conversion between Kelvin and degrees Celsius is just a matter of adding or subtracting 273.15. However, you have large chunks of people who are using degrees Fahrenheit, so there's got to be an absolute zero in this scale. So keeping vague memories of this person alive, or this unit alive, anyone happen to know what absolute zero is, or the scale where 0 of it is absolute zero given our unit system? I feel bad for the guy. Yeah, we're going to name a unit after you, but no one's ever going to use it. Rankin. Capital R. So 0 Rankin is absolute, it's the same as 0 Kelvin. And one other thing dealing with units. Questions up to here before we talk about units of heat? All right. Well, based upon my definition here, what would the units of heat be? Or what is a unit of heat? No, it's related to it, but not looking for units here. The key word. Pardon?
Joule.
Yeah, joules. However, because things are established long before standards are, or habits are established, you will often find, if you look up various bits of what are called latent heats, they don't always have it in terms of joules, they have it instead in terms of calories. CAL. And so it's just a different unit. And so 1 calorie is equal to 4.18 4 joules.
Is that at all related to food calories?
It is related, but it is not the same. Because, of course, you don't want to use the same word to mean the same thing in 2 different situations. All right, so then we get into food calories. The food calorie, with a capital C, is equal to 1,000 calories with a lowercase c. or 1 kilocalorie. Now, why? I don't know why they did not coordinate it. Perhaps, I guess our daily intake, give or take 1,000, is what, around 2,000 calories a day? And maybe it's a publicity thing. So instead of saying, if we'd stuck to the original calorie, to the science calorie, then you'd be taking in 2 million calories a day. And maybe that doesn't work as well. I don't know. All right. Now, let's connect some things here. Because we have this heat, we have change in temperature, there's a relationship between the two. Now, obviously, the more stuff I put into, the more energy I put into it, the greater the temperature. So there is a direct relationship between those two. And I left some space here for the missing things. What also matters is, since temperature actually is related to the average kinetic energy of the particles, that means the more particles I have, the more energy gets sort of distributed out. If I put 10 joules of energy into a system, the more particles I have, the lower the change in temperature. So it does sort of get spread out. And so another thing that is of significance here is the mass. You could connect it to density and volume, but they have it in terms of mass. And then this right here, known as the specific heat. And that is dependent upon the object itself. And that's part of what the lab you're going to be doing on Friday is related to specific heat, trying to find specific heat for certain materials. So let's get rid of some stuff here. And goodbye to Ray. All right. So just as an example here, the specific heat of aluminum is 0.215 calories per gram degrees Celsius. What this means is that if I put 0.215 calories into an aluminum block, then into 1 gram of aluminum, it's going to raise the temperature by 1 degree Celsius. So let's do a little conversion, just so, because you might see it's written differently in different places. So the specific heat of aluminum, 0.215 calories per gram degrees Celsius. Well, let's figure out how many joules per gram degree Celsius it is. Well, I got a little conversion factor right down there. So I multiply times 4.184 joules per calorie. My calories cancel out. And so my math problem is 0.215 times 4.184. And if someone would be kind enough, joules per gram degrees Celsius. Since we're moving over to SI units here, so the international standard, let's do kilograms instead of grams. So how many grams in a kilogram?
1,000.
So we would multiply times 1,000 grams per kilogram. My grams are going to cancel out. So this math I can do in my head. So it's 899 joules per kilogram degrees Celsius. And since Kelvin is the international standard, how many joules per kilogram Kelvin would it be? So let's go back to the conversion between degrees Celsius and Kelvin. So 0 degrees Celsius is 273.15 Kelvin. 20 degrees Celsius, 293.15 Kelvin. In other words, all I'm doing is I take my degrees Celsius and I add 273.15, often just shortened to 273, and that gets me Kelvin. So if I'm converting this into joules over kilogram Kelvin, what's the number here? It's simpler than you think. No. I guess you divide it by 273.15?
Yes.
Yeah, the trouble is that you're not multiplying by 273.15 to go from one to the other. You're adding.
Oh.
And I will say, if you're pulling out the calculator, you're thinking about it wrong.
Would you just add that number?
No.
Is it still the same?
It is. Because what we care about is the change in temperature. 1 degree Celsius in a change is the same as 1 Kelvin in a change of temperature. So 0 degrees Celsius to 1 degree Celsius, the change in temperature is 1 degree Celsius. If we converted this into Kelvin, this would be, I'm just going to drop the 0.15 right now. This is 273 Kelvin going to 274 Kelvin. My change in temperature is just 1 Kelvin. So the change is still the same, and so that's why it is just, when you're dealing with specific heat, if you see degrees Celsius on the bottom, you can just as easily just put a K there. Questions to here before we actually bring into the fact that we have a 50-gram block of aluminum sitting right there. All right. So I'm going to pump in, just so my numbers match here. I pump in energy into my aluminum block, and the temperature goes from my initial temperature, 0 degrees Celsius, my final temperature, 40 degrees Celsius. The question is, how much energy does it take to do that? Well, it's just a straight plug and chug. Q equals MC delta T. It almost rhymes. My mass, 50 grams. My specific heat, 0.215 calories per gram degrees Celsius. And my change in temperature is 40 degrees Celsius. Celsius cancels out, grams cancels out. And so whatever we are, we're going to be left with calories as my unit of heat. All right, so that's 2,000. So that's, pardon?
430.
430 calories. And then to put it into joules, so 4.184 joules per calorie.
1799.12.
And so, just the beginning of this type problem here. Let's take water. The specific heat of water. Since water, again, is rather global, 1 calorie per gram degrees Celsius. So between 4 and 5 times higher specific heat than of aluminum. So how much energy is required to raise the water 40 degrees Celsius? Yeah, we'll leave it at that. Technically, it's approximately. Specific heat of water does change depending upon the temperature, but not significantly for what we're doing. So if we're dealing with water changing 40 degrees Celsius, again, 50 grams of water. So I've got 50 grams times 1 calorie per gram degrees Celsius times 40 degrees Celsius. Get 2,000 calories, which is 8.3, not 8.8368 joules. It takes significantly more energy to raise the temperature of the water, which is a good thing. It does keep the temperature of the earth relatively temperate. All right, questions here because we're about to combine the two things. And this will relate more directly to the lab. Perfectly insulated material. I have a container made of perfectly insulated material. What I mean by perfectly insulated is that there's going to be no energy exchange through the walls. Matter of fact, we're going to seal it off at the top also, so we'll magically be able to put something into it, but the energy is going to stay in here. And we have water at 20 degrees Celsius. Let's make it 25 grams of water. I'm magically going to put in an aluminum cube and 50 grams of aluminum at 60 degrees Celsius initially. So this is my initial temperature for the water, and this is my initial temperature for the aluminum. So conceptually, what's going to happen? I take this, I have water at basically room temperature, and I stick a hot aluminum cube into it. What's going to happen?
Water's gonna heat up. The water's gonna heat up.
And
The temperature's gonna change. Would it? Temperature's gonna change.
yes, to both of those things.
The cube will cool down.
Yes,
Yeah.
that's the other piece I was looking for.
Now, since the aluminum takes less energy is it to heat up or to change in temperature?
Change in temperature.
So would it cool down, would the cube cool down before the water ever heated up? If you put in a hot cube?
Oh, close. Your wording's off though. It's not, they will start changing at the same time. But the aluminum's going to cool off more than the water will heat up.
Okay.
If you have the same amount of material, it will. Now the fact that I've got twice as much mass for the aluminum as I do water, it's going to be a little bit different. But in this case, because the specific heat of aluminum is between 20 and 25% of that of water, but I have only twice the mass, the aluminum cube should cool off more than the water will heat up. Now the reason why I wanted the other piece of it is the fact that I want to emphasize energy is conserved here. That I have energy flowing from the cube into the water. So I know that Q for the aluminum plus Q for the water is equal to 0. Because any energy that the cube loses, the water gains. And what is the formula for Q when we're talking about changing temperatures? What does Q equal? Yep. So this is the mass of the aluminum times the specific heat of the aluminum times the change in temperature of the aluminum plus mass of the water. I'll just put W for now. Specific heat of the water times change in temperature of the water is equal to 0. The M's and C's we know. So mass of the aluminum is 50 grams. Specific heat, 0.21